So with that, I'd like to introduce Mr. Lee Boysel, and let you take it from there.
Thank you. I must admit, you're very compelling when you get on the phone and you try to convince somebody to come back. So my first reaction was, oh, I don't need this. And you convinced me to come back and give a pitch, and the more I thought about it, the more I thought, you know, that's going to be a pretty good idea, especially for you young budding entrepreneurs. And my understanding is that the university is now taking it very seriously. And what I'd like to do today is go over a little history, blend it in with a lot of ideas that I wish somebody told me when I was here in terms of starting a company. And also, of course, you got the free lunch. I mean, I understand that's why most people are here. It's a great draw, great draw. Can't beat a free lunch.
Everybody shake their head no at this point.
Who says that? Anyway, I got a lot to cover here. My understanding, I'm going to have a lot of slides up here, and some of these are historical documents, and they don't exist anyplace. You will not find a lot of this information. This is the first time it's been shown. So my understanding is that you're going to stick this up on the web, so if anybody wants to look at some of this stuff afterwards, is that correct?
Yes.
Okay, if you'll figure out where you're going. Bear with me. Last time I gave a presentation, it was slide presentation. Oh, I give a great slide presentation, all this modern stuff. Anyway, what I want to talk about is an 8-year gap in history. And it all started when I graduated, yes, back in '63. And the courses that I took in logic and circuit design were vacuum tubes. Yeah, don't laugh. Vacuum tubes rip. For those of you who don't know what a vacuum tube, that's a vacuum tube, okay? And they were big and ugly, but they at least worked. And computers were made that way, and actually I came through the lobby and I actually saw a vacuum tube computer out there, which, oh, was dear to my heart. And what I want to do is tell you about how in an 8-year span we went from a transition from vacuum tubes to transistors to the invention of the microprocessor. And you say, how in the world could you make that jump in a mere 8 years? Well, I'm going to tell you sort of some of the things that went into making that transition. Fairchild has just invented the planar process, and as far as I'm concerned, those are the real transistors. Mesa's, that's not transistor stuff. And they sort of stuck a couple of devices together for an IC. Now over here we have Intel that had just announced the microprocessor. In '71, TI quickly followed suit, and TI would later say, no, they actually were there first. And little sleight of hand there that few of us know about. But then later, TI would come back and want to get royalties from all the companies on a usage patent. This is billions of dollars worth of usage. In other words, Intel wouldn't pay the price, the microprocessor royalty, but if you put one in a car, you'd pay the royalty, a toaster, a TV, so you could see that every company in the world literally was going to wind up paying these royalties. This wound up into being a monstrous who invented the microprocessor fight that ended suddenly in '75, and we'll sort of talk about that at the end. Okay, let me get back to my... Oh, I forgot to mention, I graduated from Michigan with a solid education in vacuum tubes, but I also had a burning desire to be an entrepreneur and start my own company. Now I know all you folks want to start your own company right now. Trust me, back then, I was really all alone. Nobody ever even thought about starting it. There was no VC world. It was nuts. And I was called nuts for most of my career, and it was just fine with me. It's a tag an entrepreneur can wear proudly. Anyway, I got out first year, Horace Greeley said go west. I went out there and went to work for an aerospace company, Douglas Aircraft, a bunch of 10 benders. And they made great aerospace stuff in those days. Hope we don't have any McDonnell Douglas people here. But they made launch facilities and the like, and they made first stage boosters, and they actually flew vacuum tube servos. And believe it or not, they were incredibly reliable. You never try and replace them with, yes, vacuum tube servos on a rocket, and they work great. So don't give me flack about my vacuum tubes. At any rate, I went out there and I wanted to get a quick education, and let me tell you, drink from a fire hydrant. I learned more faster than you can believe. One of the problems I had was they didn't have anybody who knew what a transistor was. Well, I graduated from Michigan, I at least knew what a transistor looked like. So they put me in charge of the whole launch sequence program. Crashed my security clearance through, and I ended up on Johnson Island in the Pacific. Just the middle of no place, let me tell you, with this launch sequence thing. And you really find out about the real world. Now, I knew that 50% of my education was going to be, or my major, was probably going to be obsolete in 3 to 5 years. 3 to 5 minutes? Bottom line is, if you find yourself behind, you go out and you get yourself a bunch of books. I went out and got every book I could on computer transistor logic, and essentially gave myself a crash course education in that. And it actually worked. I survived. And one of the bennies of working for an aerospace company, of course, is that when they would end programs, they'd throw all this surplus stuff, millions of dollars worth of things, on the open market. Well, being an employee, I had first shot at it. And what I wound up doing was pennies on the dollar, putting together probably the finest home lab you can imagine. I mean, this thing was first class all the way. And I actually used that throughout my career and actually started my company with that same lab. Moral is, if you get some kind of an opportunity like that, go for it and take advantage of all these little weirdnesses that you can get. Now, some tips for you budding entrepreneurs. First of all, my suggestion, you get that first job, don't go for top dollar. You want to go to the place where you can learn as much as you can, as fast as you can, and that's really one of those critical things. And secondly, take some of your secondary courses like ME and accounting seriously, because they can really help you out there. You're always building things mechanically. There's always, trust me, there's more mechanics than you can believe out there. There's materials and there's whatever you're building, unless you're one of these software folks that's going to go page route. You got to build something, you got to put it in, you got to get some money for it. So it really helps to know what's going on there. And as far as accounting goes, you better know your way around a P&L balance sheet or you're going to be in deep trouble. So some of these other courses that aren't really related to electrical engineering or computer science, and take them seriously. And another thing you've got to realize up front is that you're going to spend 15, 20 hours a week extra if you're going to stay ahead of the pack and you're going to be an entrepreneur. And you're going to have to pay that price throughout. If you start a company, you're probably going to be putting in 100-hour weeks. That's the good, the bad, and the ugly of starting a company.
Much like being a student, isn't it?
Trust me, when I was here, I was a flake. Okay. I saw a lot of the local bars, and at any rate, after I put my year in out on Johnson Island, that all worked out, and I came back and got myself a staff job. And staff jobs are really good because you get a chance to see a little bit of everything. Very cool. And I got to look at all these proposals and things that were coming in, and essentially they would come in. I developed a strong interest in inertial guidance systems, especially strap-down guidance systems, platforms and the like, where you use serial computers called DDAs. And DDAs are really cool things. They're serial and it turns out they're just ideal for strap down, where you've just got accelerometers and rate gyros. And one of the other things we did, of course, is we got presentations. We had a list of presentations from all these little mini semiconductor companies. Well, a little company called GME came in, little Fairchild spin out, and they dragged along their CTO, Frank Wanless. And Frank Wanless, I consider the closest thing to the father of MOS, today's practical MOS that you've got. You have never heard his name, you probably never will. I think he actually holds the CMOS patent, but you've never heard of him. But he was really one of those rebels, like I ended up being, that pushed MOS in the face of a world of bipolar. Let me tell you, there was a fierce battle that went on for those 10 years. At any rate, he came in, and they gave their usual spiel. And afterward, he knew I was interested in ICs. He came up, hey, I got to show you something. And he held up this little TO5 can. And he said, I got a 16-bit shift register in there. Of course, my first reaction was, yeah, your dreams, Frank. And he took a while, but he convinced me that, yeah, actually, there was this new technology called MOS. I was just sort of vaguely aware of some of the physics involved. And that this stuff was going to revolutionize the world. Of course, my mind immediately jumps to the drawing on the left. Those cards up there, that's the way aerospace companies design stuff. Each one of those is a 4-bit. Those are discrete cards. Remember that? They're ugly, but resistors, capacitors, all that stuff on there. And very expensive, very pricey, bulky, hot, and not reliable. You could replace it with some ICs. ICs were just beginning to appear. They were hot and they ran hot, sucked power, and were very expensive, and you probably couldn't get your hands on it. Or we had this brand new technology called MOS that allowed us to cram 16 bits of shift register on a single chip. Let me tell you, I was absolutely hooked. I wanted to be an MOS designer. Okay, some tips for you folks. Staff jobs can really be good. A lot of times you come out of school, you get narrowly pigeonholed in a project, and you can't really see the forest for the trees. It's really nice to be able to back up sometimes and sort of look at the big picture. It can really help out. If you're going to be an entrepreneur, you sort of have to get the lay of the land and find out what you can make a buck on and how you can figure out to start a company that actually will work. Second thing is attach yourself to a high-tech mentor if you can get it. I jumped on Frank Wanless, and it was the best thing I ever did. I wrote it for all it was worth, and he was my mentor, no question about it. And of course, the last one is when the opportunities for advancement learning or whatever you're doing are at an end, you move on. Now, in the old days, today everybody moves on all the time. But in the old days, it was you went with a company and you stayed with them for long periods of time. And the idea of job hopping was just not in the cards. But only do it when you really have run out of things. Well, I wanted to be an MOS designer, and I knew I couldn't do it there. So I looked around for places where I could do my MOS design. And the first thing that came to mind is Fairchild Semiconductor. Fairchild was the pinnacle of high tech in those days. It was really a with it place. And I wanted to go there, but they didn't have any activity in MOS. They weren't doing anything on that. So I wound up taking a job at, of all places, IBM's FSD division, Federal Systems Division down in Huntsville, Alabama, weird place. But in those days, IBM was making the instrument ring, which was a ring that went on top of the Saturn moon rocket, and it had all the computers and telemetry in it, and the wires ran down into the system and ran it. So the telemetry folks had a couple $100,000 worth of technical development money, and they wanted somebody to come in and look around at next generation bipolar or analog gates, and MOS was sort of what you used for the best analog gate. And I got the job. Well, I was there a couple of months, and I went in with a design that sort of blew their mind because it was the Swiss Army knife of telemetry. It was a chip design that included an A to D, a D to A, multiplexers, you name it. And I convinced them that they should go to General Instrument, where my buddy Frank Wanless had gone. And GI was the only place really making big-time MOS at the time. And I convinced them to make that, to fab that device. And the agreement was that GI could sell our product after we'd finished. So 4 months later, gave them the design, and 4 months later, went up there and spent a week in the factory with Frank. And went all over the factory floor. He was pulling wafers, he was doing diffusion. I mean, this guy was everything to MOS. And he knew how to do just about everything, and I got to watch everything, you know, scribing, dicing, die attach, the whole smash. We packaged up some of the first chips, this A to D, and came down on that thing. You can see the picture on the right-hand side there. It's 100 gates on a chip, and it's, as I said, the Swiss Army knife that sort of does everything. And worked perfectly. And Frank was like a kid in a candy store. He just absolutely was so excited because he was a process type, and he didn't know how to design systems and circuits, but he knew that was the first time anybody ever put a system on a chip. Other than that, there have been some shift registers out of MOS, but this is the first real life system, and he was really excited about it. And while I was up there, he ended up giving me all the tips on processing circuit design, you know, random parasitics from the process, as well as teaching me how to lay my own masks out. Masks were a big deal in those days. And interestingly enough, after that week I spent up there, I went directly to Solid State Circuit Conference in Philadelphia. And that was really interesting because I was sitting there in this auditorium, and of course you've got all these semiconductor luminaries up on the stage. And one of them was Gordon Moore, you know, who at that point in time ran Fairchild's R&D department. And I remember Gordon Moore, you know, Moore's Law and all that, that's him. He got up there and he said, someday somebody's going to put 100 gates on a chip. And I happened to be sitting in the audience with this very card in my pocket. 100 gates, and I wanted to run up the aisle and say, no, Gordon, we did it. And, but 2 years out of college, trust me, discretion better be the better part of valor. You think about things like that, but you don't do them, okay? So, cool. But anyway, it was fun. I knew we were cutting edge stuff at this point in time. Anyway, went back to IBM and designed a second circuit. And at this point in time, we had, you guys have to appreciate this because today you have CAD. CAD was something in the neighborhood of 10 years away. The way we did our masks, this is a real live, honest to God mask for you folks. It's a piece of Mylar and we put all 4 layers on it. MOS was simple in those days. We had P regions, you had gates, you had contacts, and you had metal. Okay? And we'd lay these things out, and the dash lines were the metal, and the solid lines were the P regions / the gates, and etc. So we lay these things out, and then we put on these big cutting tables, big light tables. And you'd essentially go along with a knife, and you would cut out the particular mask that you were making. And to the right there, you can see the metal mask that was the result of cutting out of this circuit. That is the metal mask for this one. And in those days, you know, as I said, no CAD, no automation, anything. We took a picture of that, and then we stepped and repeated it, and ignoring the blooming and the blowout and the misalignment and everything like that, you had to design with pretty sloppy tolerances. We actually made stuff that worked, and it worked. Now, in the meantime, while I was doing all this MOS design work, which I loved, I was also taking a very close look at IBM since I worked there. I got a very close look at their mainframe architectures. And one thing that occurred to me is that where I'd been interested in MOSing, turning a DDA, serial computer, which is a natural for LSI, I suddenly realized that a parallel architecture was going to be pin minimal to any kind of serial design. I know that's counterintuitive, but that's the way it goes. I also found out that microcontrol, magnetic core microcontrol, was the other way of minimizing pins. Now, in the old days, it was really ugly. You had a bunch of magnetic toroids like this, and you just wove wires through them. If you wove the wire in, it was a 1, and if you didn't, it's a 0. Trust me, it's crude, but it actually worked, and that's the way IBM's mainframes worked in those days. So, an interesting thing happened along the way. Right in this area right here on this circuit I was laying out, I wanted to make sure that the circuit was reconfigurable. You know, I like this Swiss Army knife approach where everything from soup to nuts. And by just changing the gate mask, I wanted to allow the thing to be reconfigurable into a bunch of different configurations. It was a differential low voltage analog multiplexer. Only time I screwed around with analog, and I'm telling you, it's really tricky. I pity you RF folks. How do you make that stuff work? I do not know. At any rate, the one thing that occurred to me is I had these P regions, I had these metal regions, and by just changing the gate mask, I could essentially reprogram the thing. Voila, suddenly it occurred to me, that's a read-only memory. Well, at that point in time, I knew I wanted to design my own computer because every engineer on the planet wanted to design their own computer, trust me. In those days, you didn't buy micros or anything, everybody wanted to do their own, and I was no different. I wanted to design my own computer, and I knew that a read-only memory was going to be the core of it for microcontrol. So, some tips for you folks. If you get that floor experience like I did with Frank Wanless, really very helpful. Get down there and get your hands dirty and find out what it's like. And watch as much as you can, because a lot of time engineers tend to sit in their offices and the like. You really want to get down to the factory floor and find out what's going on down there. Trust me, you know, that's where the money's made. And if you're going to make your million, you better be aware of what the product is, who the customer is, and why they're going to give you money for that thing. And the second thing, again, if you're out of opportunities, move on. And at this point in time, I designed practically, well, every telemetry thing you could find, and I wanted to design my computer. So I started looking around again, and this time, when I went to look around, Fairchild had decided that they wanted to pay lip service only to MOS. So they had a new org chart, they had a MOS box in there, and I managed to get hired to start that. Now, no budget or anything, and of course, their objective was to have me transfer the MOS process that was developed up there in Gordon Moore's R&D magic land, if you will, down into the blue-collar manufacturing circuit area where I worked. And of course, my objective when I went there, I wanted to make my own computer. And I was going to do it. And number one on my list of things to do was to design a read-only memory. Well, needless to say, that's it right there. That's the first semiconductor read-only memory. And of course, Fairchild management, keep in mind, Fairchild at that point in time was a transistor company who was just moving into ICs. Well, a JK flip-flop was a big deal for those folks, okay? So the idea of a read-only memory system component, there was no chance. I convinced them it was a test pattern. I got away with it too. And well, until Electronics Magazine, who really knew what was going on, saw it, and they did a big article on it, and they published my article on it, and published an article about the first solid-state read-only memory. Well, wow, this is big news. A couple of months later, EDN actually magazine put it on the front cover. At that point in time, Electronics Magazine was the primo magazine. Every engineer wanted to get their articles published in there. You got published in there, I mean, it was a big deal, let me tell you. So it gave me instant credibility. So anyway, we designed that, and some tips for you folks. Really don't worry about getting your hands dirty. Turns out, when I went to Fairchild, I was so low on the priority list that I couldn't get in the queue to have my mask cut. So I went over to the cutting room, where you have dozens of people cutting these big masks, because Fairchild was just scorching hot in those days. They were the primo semiconductor company. You don't hear about them today, trust me. At that point in time, they were magical. And over the corner, they had this broken down cutting table, and I cut my own masks. The first time an engineer had ever done it. It's an old broken down cutting table, had the dullest blade that you could imagine, but somehow my margins were big enough that I could afford a dull blade, and I cut the masks for it. And the second thing is, this kind of thing can really help, because you want to learn all areas of whatever you're doing. You want to learn, you know, from here down to here, and learn all the different steps, because I guarantee you, when you start your company, you're going to be an entrepreneur, you're going to be wearing a lot of hats, you will not have a staff. And you better know everything from how to design whatever it is you're doing to how to make the coffee if you're going to survive. Anyway, that was step one. Next thing, 2 months later, came along with my the first ALU slice, and that was the biggest circuit that certainly anybody at Fairchild had ever seen, and came down on it, worked perfectly right out of the chute. Management again had no clues to what I was doing down there, where I ran sort of a funny skunk works, because the bipolar people really didn't like anything that was coming out of the MOS department. There was a war that spanned the whole industry. And anyway, that circuit came back, and once again, Electronics Magazine jumped on it, published it, and they understood the significance of it. Now, by this time, Fairchild realizes that I'm giving them some really good PR by being published a couple of articles that fast in key magazines. And I really was getting some serious street cred. And they gave me 4 recs, which I thought was pretty cool. So I went out and hired, and instead of hiring semiconductor people, which was the norm, you'd hire semi people into a semi company, went out and hired a bunch of computer people, systems types, brought them in, trained them my way. What I did was I trained them to think systems, logic, circuits, and handcrafted mask layout. And the reason for that is, it turns out, when you're doing an LSI design in those days, you know, no CAD, no simulation, no nothing, when you are screwing around with an architecture up here, you better be thinking about pin counts and silicon allocation and bus routing and everything else down here. And if you're not thinking that whole thing, you're not an LSI designer. So I wound up with the only team that actually was really capable of doing big, I mean big, LSI circuits. Now, a couple of tips for you folks. You really want to, if you possibly can, get yourself a trained team of experts to go with you. You don't want people that are going to go off and start their own thing the minute you get started. You want a dedicated team that will follow you anyplace. I swear my guys would have followed me through the gates of hell if I'd asked them. They were a team that I trained, and I took care of them. And I really took care of them. I took care of them, money, everything. I mean, I lived with them. It was not a boss team, it was a team effort. And that was really key. And made them all millionaires later on. And that's when $1 million was a lot more than it is today. It's like $3 million today. So they all retired comfortably, let me tell you. And another thing, one other thing I might mention along these lines. There's a bunch of different ways to make your million. And one of them is to do it yourself, which is really hard and it's a pain. If you can spot the guy that's going to do it and be one of those team members, you know, that's an easy way to shortchange the process and essentially jump ahead of the game. So look around for those people that you think are going to make it, and you might want to be part of their team. You can go off and start your company later on if you really want to, but up front, you may not want to. Okay, another thing, don't get hung up on degrees. I know PhDs are a big deal, and at Fairchild R&D, they were a big deal. For me, I wanted people who were clever, good with their hands, smart, savvy people. And it turns out, one of the folks I hired only had an AA degree, no degree. And he turned out to be one of the industry's absolute premier LSI designers of all time. The guy was absolutely a genius. Moral is, you want to look for those people that are creative, that don't necessarily grade well. I mean, dyslexics, ADDs happen to be my favorite. I am one, so I can say that, okay? He was too, as it turns out. And we wound up doing most of the really hairy stuff. Okay. A year later, we've designed dozens of system computer building blocks. That drawing on the right, that block diagram, which has been featured in numerous litigations. That drawing alone saved Intel millions of dollars in a RAM and a ROM patent dispute with GI later on. It turns out that that's not some mini computer. That's a 32-bit IBM mainframe. And what you can't see is those little numbers up there. Those are the part numbers that we had either done or were in the process of doing in terms of making these blocks to make this computer. I didn't want to design something small. I wanted to go right for the big enchilada. And that's what I was after. And along the way, we had to come up with a lot of new concepts. You got to think outside the box a lot of times. We came along with the second generation ALU. Turns out it had bidirectional busing. Those days, you know, you had line drivers and line receivers. So your addresses went out on one line and your data came back on another. Really crude. The idea of a floating bus output, nobody ever thought of that. Well, actually, it really wasn't practical until you got something like MOS where you could float the bus. And for pin minimization, everybody takes it for granted today. But bidirectional busing, I mean, the universal bus was just, man, that was weird stuff in those days. We also jumped all over something called dynamic logic. And that is the coolest stuff that ever came down the pipe. You'll notice this drawing, there is no power and there's no ground in there. Well, what that meant for us was that all you had to do was charge and discharge a little capacitor, and that capacitor held the ones and the zeros. Like, this is the way everything's designed today, but in those days this is pretty revolutionary stuff. And you could charge and discharge it with a minimal sized device here. Well, what that meant was we could get 10 times the packing density. And all you've got is an RC time constant there that's small. Well, certainly at the speeds we were running, don't forget it was megahertz world. We had 10 times X the speed. So we got 10 times the packing density, 10 times the speed, and of course we just have CV squared power, so it's a tenth the power, and it was revolutionary. And we went back and changed our whole design philosophy and swung into that dynamic logic stuff, and that gave us enormous power. With our parallel architecture, which gave us, we were fast just because we were parallel, and that, we were in a position where we were really threatening a lot of people. Two groups in particular. And even though I tried to have my group operate below the radar, as I said, I didn't even put a Fairchild sticker on that drawing. It's got at least 20 deposition stickers on it. It's been used in that many trials because that drawing has been vetted 6 ways from Sunday. But Fairchild would have taken offense at that. And the reason is, Fairchild, like every other semiconductor company, is stupid. They realized that that one MOS chip would replace a dozen bipolar chips. This is really bad when it comes to business, and I understand where they're coming from. That's just not what you want to do, and I understand their position. So they didn't want to be part of MOS. And the second one sort of fooled me, and that was computer companies came in and their engineers said, we don't want any part of these standard product stuff because our claim to fame is the bells and whistles that we added as the computer designers of Burroughs and Honeywell and all the big corporations. So essentially, we were building a computer that nobody wanted. I mean, it was a little bit strange, to say the least. And we still hadn't solved the solid-state memory problem. Now, this is critical. Tips for you entrepreneurs. No NIH. This is really critical. When this came along, and some guy named Joel Karp, I think, from Philco Ford, of all places, came up with this idea. We went back and changed everything. Somebody comes along with a good idea. You leave your ego at the door, and you jump on everything. My guys were trained to you steal everything that's not nailed down, okay? Somebody comes along with a good idea, seriously, jump on it. Just get your ego out of the way. And if you're going to be an entrepreneur, be a winner, that's critically important. Okay. 9 months later, solved the problem. At that point in time, all computers used big cores. I don't know if they've got one out in the rack out there someplace, but cores are the ugliest things you can imagine. A bunch of XY wires and little magnetic donuts in them, and if they spin one way it's a 1 and the other way it's a 0. But every computer out there at the time was using core memories, and you just couldn't beat them. And I didn't have any core memory or magnetic courses at Michigan, so I didn't have a choice. I had to come up with a solid state memory. And spent a couple of years working on it, so was everybody else. People from IBM and Fairchild, you name it. Everybody tried to replace the core. Nobody could figure out core memories. Nobody could figure out how to do it. Now, in the meantime, I was working on dynamic shift registers to feed video. And I wanted to introduce RAM addressability, bit addressability into those things. Well, next thing you know is, voila, it's a DRAM. So that's where the DRAM came from. Now, I thought it was a pretty weird device because it was like a RAM to the computer, but it required this weird refresh in the back. Well, I didn't care because I knew that whatever I designed as a computer, it was always going to have a video terminal out there, so I was always going to be refreshing something anyway, so what was the difference? And essentially I knew we had the last piece and we're off and running. So anyway, the computer nobody wanted to do it. I was going to build my computer come hell or high water. I was going to go out and start my own company. And my timing was absolutely perfect because in the fall of '68, Fairchild, the pinnacle of all technology exploded. And that actually is where Silicon Valley came from. It wasn't Stanford, it wasn't Berkeley, it wasn't HP, it was right out of Fairchild. There was layers and layers of some of the best talent in the industry. And it exploded. You can see the chart on the right, some of the companies that were survivors. There was at least 24 that started probably in that era. And my company, Four Faces, up at the upper right-hand corner. You can see Intel here, AMD, and you can see some of the other luminaries that all broke out of Fairchild. That's where it all came from. And it just exploded. And of course, I went out and tried to raise money. Investors thought I was flat nuts. You're going to build a mainframe computer out of doggy old MOS, and you're going to do a solid-state memory that nobody's ever been able to do? Well, they thought I was nuts. But Bob Noyce, who was Fairchild's CTO at the time, he was sort of the guru. He had the patent on the IC and the like. A couple of months before, he and Gordon Moore had left to start Intel. And at the time, I think he was Intel's chairman. And Bob knew that down in my little skunk works, much as we didn't say very much, we had some really cool stuff. And he said, that's worth the investment, and I'm even willing to sit on the board. So he joined our board of directors. Needless to say, VCs came on board. I got my $1.5 million, and we were off and running. Some tips for you entrepreneurs: get yourself good board members, and I mean outside board members. You're always going to have a couple of VCs sitting on a board. Fine. They don't really understand what you're doing. You really want to go out and get some business people, some heavyweights. I was fortunate enough to have a half dozen people, key executives on the board, and they're the ones that sort of keep the VCs in line. In addition to Bob Noyce, I had people like Jim Morgan, the president of Applied Materials, Al Dawson, number 2 at Corning, Jim Guzzi, the number 2 at Memorex, Carl Vorderbergy, the head of marketing at MCI, just a lot of people. And when the VCs get sort of freaky sometimes when you miss a schedule or something like that, it's these stage business executives that come in and sort of calm things down. You go out and get yourself the best outside directors you possibly can. And secondly, if you're worried about control of your own destiny, I want to control my company and own 51%, forget it. VCs own 30% of your company, trust me, they got control. And don't try and circumvent these guys by going out and getting nickel-dimers. By that I mean doctors, lawyers, friends, neighbors, and the like, because when things go wrong, and I guarantee they will, these folks run for the hills. And the one thing about the VCs, every time they put a buck in, they got $2 in their pocket, because they know you're going to screw up, and they're willing to come around in subsequent rounds of financing and keep you going. So that's just the way the game is played. You don't really have much choice on that. So, running tight in time here. Am I okay? Okay. Okay. We start our company. Off and running. 5 months after we start the company, we bang down on that first die. And this is the heart of the computer. This is the AL1 chip. This is the culmination of everything we've done at Fairchild all those years. And this thing was blindingly fast by standards then. It was bipolar speeds. It was 8-bit, and it had all the registers. It was literally a self-contained computer. And it was the smallest size you can imagine. It's 120 mils. It was the last circuit that I actually laid out, and I contend you can't cram one more transistor on that thing. It is as solid a hand layout as you can get. And hand layouts, incidentally, will always be the computer layout. You wouldn't believe what the human mind could do. But anyway, it was small enough that even though we were using 1.25" wafers, I know that's laughable because you use wafers this big these days, we were getting yields that were so high, you could see the yield pattern on this thing, that we wound up at $3 a chip. Well, the interesting thing is that Bob Noyce, who was chairman of Intel at the time, walked out in the lab, and the VCs would always send him out because he would tell them whether we knew what we were doing or not, because he was the techie sort of lead for the board. And he went out and he looked at that, and he looked at the yield, and he's a visionary. He really was a visionary, and he realized that if Intel were going to move ahead, they were going to have to look at a lot of different options besides RAM and EEPROM, which is all Intel did at the time. And he saw that that computer chips were going to become commodities. It was really visionary at the time. And he went back to Intel and actually headed the development, the setup of a computer group. And I talked to him, and he went out and hired systems people, not semi people, brought him in. He personally got involved in the hiring of people like Ted Off, these computer architects out of Stanford. And essentially, Intel took a turn at that point in time. Now, the interesting thing is, since they took that turn, today, of course, they don't sell ROMs and they don't sell RAMs. But they're king of the hill. They're the 800-pound gorilla when it comes to microprocessors. And it all sort of started when Bob just said, wow, you know, this is commodity stuff. And so there's a little history behind that thing. Let's see. Okay. A month later, the other game-breaking chip came back. Banged down on it first time, worked perfectly. It was our 1K DRAM, because this is what we were going to take cores on with. And this thing was really revolutionary at the time, let me tell you. And came down on it, worked great, and it was interesting because the yields appeared to be high enough that we were going to get into 10 penny bit. And we made it sloppy enough so it worked. Our circuits had to work. We didn't have time for reworks and the like. They had to be right out of the barrel. So we made them pretty sloppy. Well, it worked so well, we immediately swung into 2K RAM, which was our workhorse from then on, and actually lasted in the field for, actually they're still out there today, believe it or not. I kid you not. And at that point in time, we hit a ½ cent a bit, and the handwriting was on the wall. Core memories were going to be roadkill in the not too distant future, and that's exactly what happened. I mean, it was over. We had finally cracked the magic barrier. And it was interesting, because once again, the board sent Bob Noyce out there, and I remember it distinctly. He came out in the lab, and he looked at that 1K die, and he took that scope. We were running an X pattern in there, and he was counting those bits. He could not believe that some dingy little computer spin-out was sitting there making a RAM that was 10 times bigger, the biggest thing that Intel was making. Needless to say, he went back to Intel, raised holy hell, and Intel's MOS memory business went like that, and they swung around to DRAMs, and at that point in time, it changed Intel substantially. Now this is really good for us because at this point in time, we were running around telling people we had this memory that required a refresh. Well, when Intel came along with it, we were golden because that gave us all the credibility in the world. Now, as far as some tips for you VCs, some good PR in the public and public recognition can really help. VCs tend to be a bit incestuous. You go out to Sand Hill Road, these guys all have lunch with each other, and it's very chummy stuff. But they're also very competitive. And they like to go out to lunch and they like to brag about their investments. Now there's nothing like them going out and holding up a magazine article, hey, my company just got the front page of this stuff. It can really help in subsequent rounds of financing. Let me tell you, it really helped us. And the fact that obviously this you know, the first solid state memory that had ever been built in a computer that actually worked, well actually it's the first one that ever been built, work or not, made the front page of Electronics Magazine and EDN. Let me tell you, we really got some good press on that because that was really sort of a watershed moment in the computer industry. And all this is a 69 type date. Okay, a year later, a dozen complex chips come together. Now keep in mind, you can't breadboard this stuff. There was no simulation, no CAD 5 years out at least. And we put all these chips together and I'm the great optimist, and even to me, I was shocked. The whole thing worked perfectly. We never had a redo on a chip. The whole thing worked together. But in addition to things like the ALU and the memory chip, we also had I/O chips that were designed for performance improvement. One of our chips was a true 8-level, true nested priority interrupt chip. It was the hairiest logic I'd ever been involved with, but we finally figured out how to make it work and not lock up, because it's very intricate if you think about that. The advantage of that chip is that just dramatically reduced the amount of I/O software overhead we had and speeded the machine up. Well, all of these chips, a lot of these chips we did that for, and we wound up with a computer, even though we're using this old 28-volt metal gate process. I mean, there was nothing magic about this. This was blue collar as it comes. We were, through design, through engineering design, able to create a machine that was as fast as a mid-level IBM mainframe. And I mean instruction for instruction. We ran the same kinds of instructions, strings, decimal, floating point, you name it, and we ran bit for bit as fast as the $250,000 IBM Model 30. I mean, that's a great big blue box that sits in an air-conditioned room. And in addition to that, we could run 32 terminals. The little claims to fame like this are really important, without any overhead. And the reason for that is because we had solid-state memory for the first time, we could put an A in a dedicated location in memory. Now, in the on cycle, when we were refreshing this thing, our circuits would come through, convert it to dots, and then we'd turn it into composite video, and we'd shove it down a coax, plain vanilla coax cable up to a half mile away, where there'd be a dumb monitor. Well, the A would immediately appear on the monitor. Well, what that meant is software people could write programs that just, you change the memory, you change a character in the location in memory, it's automatic, there is no I/O, it just appears on the screen. We called it a window in a memory, and it allowed us to run up to 32 terminals with no I/O overhead. We could instantaneously change all 32 tubes in 30th of a second, which is the total horizontal refresh on a CRT. And by comparison, you take an IBM $1 million, the big 65s that they had in those days. This is old stuff, but bear with me. Concepts still apply. And you put a couple of dozen terminals on there, people start paging through memories, you eat those machines alive. It's brought to their knees with I/O overhead. So as a result, we knew we had a big advantage. Now, in terms of what we did during that year, we put a fab operation in. Put the whole thing in for $300,000. Probably cost you 30 mil today. What does it cost? Or this one in, I mean, they cost anywhere between 30 and 300 million, depending upon who you are and how big you want a fab operation. Really cheap in those days, very simple, but it worked. You see our memory card over there and CPU card. The 12 chips there was 3 of them. We had 3 ALUs, AL1s on there, that power CPU processor to make the thing faster, and we had some other chips on there. And that was sort of the core CPU in the I/O area. And once again, we kept our VCs and financing in mind. And we came up with an interesting gimmick. Still 12 chips. We took those 12 chips and we put them on a little tie clip. I know nobody wears ties today, but in those days they did, and they wore tie clips. Well, these 12 chips literally are exactly those 12, and our yields were so high that these probably work. And what we would tell VCs is, if you invest in our company, we'll give you one of our computers. Well, needless to say, this became a really hot item in the VC world, because these guys would go down to Sand Hill Road or wherever they had lunch, and they'd put their tie clip on, and what's that? Well, that's my computer that Forfays gave you. I know it's gimmicky, but trust me, when you're dealing with VCs, they like weird stuff like that, okay? Anyway, that was a real winner for us. You can see the computer down here that we had, and CRT, and that little box right there was the equivalent of, the IBM big Model 30, and also included the ability to run 32 terminals. Just that little box. And didn't require air conditioning. You throw it on a shelf, you throw it in the closet someplace. I mean, this thing was bulletproof. And literally, our salesman would demo this thing by throwing it in the trunk of their car and driving around, and they'd come out and demo it, and the people would just be stunned that the salesman would come in with a demo, plunk it down, plug it in, and actually run programs for them. So it was a big deal in those days. So less than 2 years after we got out of Fairchild, I finally got to design my own computer, and that was a lot of fun. But we also had to use completely new technology. We still got the whole thing to work, up and running, and made the announcement Fall Joint Computer Conference, and actually got our first order from Eastern Airline. That's the days when Eastern Airline was big airlines, and I don't even know if they exist today. Anyway, tips for you entrepreneurs. You've got to move fast. Always assume that your competition is right on your heels. I kept telling my troops, the competition is probably 2 or 3 months behind us. We've got to go, go, go. And we pressed, I mean, it was strictly, we're talking 100-hour plus weeks guaranteed for everybody there to make this whole thing happen. And it's really critically important that you do that. Now, it turns out that our competition, before anybody came along with anything even remotely close to what we had, was 3 or 4 years. But I didn't know that at the time. And this is why we were successful and our competitors weren't. So that really made a very big difference. So one of the things that you budding entrepreneurs should stick on your forehead is only the paranoid survive. I'd like to take credit for that, but Andy Grove came up with that at Intel. And it's the truest thing going. You have to assume that whatever you're doing, however cool it is, that some guy in a lab halfway across the world or halfway across the state has got something that's about as good, and you better be moving fast, and it better be good, because they're going to be right on top of you. The idea of sitting around on good ideas, they don't last, trust me. So, a year later, Intel makes the announcement of the microprocessor, certainly the first commercial microprocessor. TI follows suit. Now, that same year, Four-Phase shipped $3 million worth of AL1-based computers. We literally dominated the terminal market, and we almost single-handedly wiped out the key punches. You folks remember what a key punch is? It's that ugly-looking card that's got all those holes in it. Well, that used to be one of IBM's big markets. It just went away. People entered directly into these CRTs. They were so inexpensive and became very prolific at the time. We dominated markets like hospitals, where you take one of our computers, you throw it in a closet in the basement, and these cables, our coaxes, would run up through the elevator shafts, and there'd be 50 or 60 of these terminals on nursing stations and in pharmacies and in doctors' offices. There had never been hospitals with any kind of terminals before. It was just prohibitively expensive. There was just no way it was ever done before. So this was a new deal. We had 3 big corporations that used to sell hospital systems, HBO, Shared Medical, and McDonald's. And all 3 of them discreetly had to use our machines, because there was nothing else that could even come close to the ability to handle all these terminals in all these locations. Dominated that market, dominated big data entry areas like Social Security Administration and IRS. And incidentally, until the year 2000, all of your tax returns have been processed on our machines. These are machines, 28-volt P-channel stuff. Trust me, this is old stuff. And the reason that they had to replace it in the year 2000 is because we had a 2-digit year code. Well, 25 years ago, it never, ever would have occurred to me that the IRS and everybody else would keep our machines in for 25 years. You've got to be kidding me. Gee.
So the Y2K problem, who's at fault, we now know.
It wasn't us if you got an IRS problem, because we were out of there. They knew that we were going to bomb them on Y2K. That's exactly the problem we had. Anyway, the company went on to be a Fortune 1000 company before it was acquired by Motorola, and we probably had 100 competitors in the 70s, and by virtue of the technology, we just wiped them all out. Moral is, if you get yourself some technology and you're running a company, you have to be brutal to your competitors. You have to go after them. You have to take that technology, and you have to seriously pound your competitors. And when you have a technological advantage, that's how you wipe your competitors out. Hate to make that sound so merciless, but that's the way business is. It's pretty brutal out there. It's sink or be sunk. So, anyway, why wasn't all that history available to people? I mean, nobody really knows about that stuff. These pictures haven't existed. And the answer is sort of twofold. Number one, we didn't want to talk about it because our customers want to deal with computer companies. They didn't want to deal with some semi company. And secondly, we pulled out of Fairchild, and so did everybody else. Fairchild sort of disintegrated at the time, and all our records and everything we had done, and all these magic inventions that actually were done at Fairchild, were sitting in the filing cabinets. Eventually, they just threw them out. So all the records were lost. And of course, people like Intel, they want to tell history the the way it favors them. And I don't blame them. I mean, that's where their marketing is. They sort of ignore those 8 years. It's just Intel just suddenly invented the microprocessor. Well, let me tell you, the microprocessor just didn't come out of nowhere. Now, all of this history would have remained buried, except TI raised his hand 10, 15 years later and said, but we invented the microprocessor and we want billions of dollars in royalties. So let me jump ahead and put a capper on this. Sort of the epilogue of what happened years later. And you got TI running around suing every major corporation for usage. And this battle raged for a long period of time. And one of the things the lawyers, and there was dozens of them, when I got involved, I was the expert witness for 25 different legal firms. That's how many people, and those were just the people that were being sued up front from TI. And the one thing that they kept running across was this AL1 chip. That kept copying up as prior art. And of course, it had never been mentioned by TI in any of their disclosure to the patent department. So they came to me and they asked me, what's the story on it? I said, well, I pointed out to them that in the depositions, that all the engineers from both Intel and TI had admitted in deposition that they had essentially read all my articles, that one described the AL1 in great detail in computer design, and had copied and used all that information. Well, TI's lawyers were very clever, and they went out and got themselves a bunch of expert witnesses, Stanford professor types. No Stanford people here, are there? And they were willing to get on the stand and say, well, whatever the L was, it wasn't a computer. Well, needless to say, this really irritated me. And I decided to go out and build myself a computer model, which I did. You can see it on the right here. And essentially, I took one of our AL1 chips, and that chip has got a 1969 date code on it that's been vetted. I mean, everybody agrees it's a 1969 date. And I took the patent, and the patent says there's a ROM and a RAM and an I/O. And that I/O is just a UART that goes out and talks to a dumb glass teletype. That's an old glass teletype for you folks. No computers in there. And it would sit there and run business programs that ran the same software that DataPoint, the company that originally instigated the Intel and the TI parts, the software that was supposed to run on their machines, the test software, I was running here. So there's no question about the fact that this was compatible stuff. Not only that, this machine ran 20 times faster than the first micro from Intel or TI. So that immediately explained why we wouldn't sell it to anybody when they came to us, because I'm not about to give a microprocessor that powerful to my competitors. No wonder we didn't sell it. Of course we didn't. But it still counted in the patent war. Anyway, a week before the first trial, this was Dell, and I think Samsung, Daewoo, and Tandy were lined up trial-wise behind them. The lawyers asked me a fatal question of the last day of one of my depositions, and I told them about the computer jury demo model that I made, and faces went white, place turned into chaos. It's a wild story what happened, but they went back to their expert witnesses and told them about this model, and their expert witnesses said there's no way that they were going to get up in front of a jury, in front of these big monitors that our lawyers were going to put in there, running games and solving puzzles and playing and doing business processing just on that little computer. They weren't going to tell them it was a cabbage shredder. There was no way they could do it, and that whole 8-10 year litigation ended that week. Bang! It just suddenly fell off They just realized that they'd lost, and it was over. So I like to think that little model saved JQ Public, you folks, $4 or $5 billion in unnecessary royalties that you would have had to pay, tack down to your car and your TV and your toaster and everything else. So they got my attention on that one. Okay, I got stroked on that one. One interesting side to that is Intel's tagline used to be "Intel invented the microprocessor in 1971." You notice right after that they changed it to "Intel invented their." They added an IR to the microprocessor in 1971, and that's the way it's read ever since. So you want to know what the first microprocessor was, you're looking at it right there. I mean, that's the one that ran their software, ran it 20 times faster, and was sort of the first micro that ever came along. So anyway, that didn't have much to do with being an entrepreneur and stuff, but I'm telling you, it can be fun. I know it's a lot of work, and the rewards can be terrific. You know, there's the good, the bad, the ugly. You make lots of money, you have to work hard as can be, and there's all kinds of health problems and everything else that certainly hit companies like mine, where you've got people that are so stressed that they get into trouble. But in general, it can be a lot of fun. I strongly suggest, if you've got the urge, go for it, no matter what anybody says. And along the way, if they say you can't do it, you just show them you can. Anyway, if you got any questions, I think I overran my time substantially. So my apologies for all you folks that got classes right now.
Well, first off, let's